Good evening, folks. Is there already people here? We're actually a bit early this week. I've been late the last few weeks, so it's like, let's make an early appearance. Let's see, Nigel Tech 49 was here first with hello everyone at 8:30 already. He's been waiting a while. And then Uma Kavala was here at 8:52. And then Moonlight Shaker. I haven't seen him before, I think. And then Gareth Blaine and Kvik DK. Noise. I'm still messing with my desk because it's become such a mess for a while now, and I still haven't cleaned up because all kind of stuff is going on, and you know how it goes. At some point I'll be so annoyed that I'll actually clean it up, but that point has seemingly not been reached yet, or at least other stuff has been more important. Oh well. Hey, why is this LED strip here? Nobody wants this LED strip here. Good evening, everyone. Heckamos. This doesn't really need to be here now, does it? No. Okay, well, this is nice and warm. Good. Okay, I have room to move. Nice. Yes. Who knows? Today we're going to continue the WPS project, the wall panel sensor, and maybe if luck has it, or I don't know, if we work hard enough, we might actually get to the PCB stage. So we will be freed from our eternal damnation in the schematic and scouring for components and making connections and stuff like that. And then we'll be able to actually route them on the PCB and make it something physical instead of just logical. So, sorry, I'm just annoyed by everything that's on my desk, all kinds of little screws and... Anyway, how is your evening so far? Is it evening where you are? I don't know. Missed a few, so excited to see this. Nice! Oh, the music is still very loud. Well, we're still in the pre-stream. It's okay. Let's see. There we go. UK here, so it's 2000. Okay, well, it's 2100 over here. Let's select a drink, because I can drink in the pre-stream. Oh, no, what's going on? Oh, we're sharing the screen that also has the chat. But double chat's a bit redundant. So I'll move chat over here, and we don't need this right now. No, I don't need. Yeah. So the drinks. I have a special friend who always a very kind friend who always brings me very special drinks. So today we have new stuff. We have Pepsi Zero Sugar. That's good. Cream soda flavor, or we have Pepsi Zero Sugar. Cherry and vanilla flavor. What? And we have Pepsi Zero Sugar, raspberry ripple flavor. I like this one. I like them all. I think I like this one the best. So I'm going to drink this one first. That's how it goes today. Correct size cans. Yeah, these are 330 milliliters. But these are actually from Great Britain, because she was on vacation in Great Britain, and she bought me a 6-pack of each of them to take along, and I can drink them and show them off in the stream. So that was very kind of her. If there's any secrets today, well, you might see some weird flashing lights and things like that, and we have some... let me see if I can make this appear on the screen. There, we have some light bars which are glowing. Oh, look at that. These have been in test for a few days now. And these are, if everything permits, the final prototypes for the V4 series for the Dig Uno, Dig Quad, and Dig Octa, because I hope to get those into production really soon. So I guess, I don't know, I'll show those off after or at the end of the stream. Yeah. Is this one still blinking? It is. Good. Cherry vanilla, best of both worlds, right? Yeah, I guess. Yeah. But the raspberry ripple flavor I also like. It's very good. Oh. So, let's zoom this out a bit again. I don't know. Oh, it's really smelly. It's like you open it and it's instantly on. It's PCB time. Well, no, we have to finish the schematics and then assign all the components. And then it's PCB time. But last week I actually figured out that we missed something on the schematic design. So we have to assign some pins for that at least. But we took a much broader cable, so I think we should have those pins available. But we'll see. We'll see. Oh, right. It's obligatory. Do we need to update KiCad time? Let's see. Let's see. It's been 2 weeks, so who knows? Let's do this. There. KiCon Europe is coming September 7. Oh, okay. Where is it? Where is this? In Bochum, Germany? I don't know where that is. Your logo here. They don't have a lot of supporters yet for something that's in September. They don't have any supporters. How do you become a sponsor? Let's see. Oh, 10,000 euros, a bit much. Okay, you can get a supporter for 500 euros. 1,500. I've donated more than 500 euros to KiCad before. Oh, and oh, okay, yeah. On the name badge. Okay, where do we get a banner? Sponsor logo on conference banner. 20. That's a bit rich for me. Okay. Oh, you get an exhibition space. I can show my Queen LED stuff. No, that's not. Anyway, we're going to see if there's a new version. July 22nd. Nope. We have this version. How far are you on this project? You mean the wall panel sensor? The exactly where we left off? or do you mean another project? I had a headache the whole day, and it's finally lifting, so I'm in a good mood. If I look to the right of me, I only see rainbows. Oh, sleepy. Oh, you know, it's okay. You can always watch back if you're really interested. I won't blame you if you don't. Oh, you missed a few, so you have no idea where the project is. Well, we'll see in the schematics editor, but most of these schematics are now complete. So for the PUE power supply and the buck converters and some other things we needed. And then we're going to match component footprints and like resistors and capacitor sizes, things like that. Part of that is already done. And then once that is done, we can start on the PCB work. So we have to first figure out the size of the PCB and then where the connector goes. I think that's important too. And after that, we get to do the layout and routing and things like that. And once that is done, it's probably 1 or 2 streams that we need to do that. It's not too complex. We can order our first test sample. No new versions. Good. I guess I can make this a bit bigger. I don't know. Should I make it bigger? We'll see how it goes. If stuff isn't hidden behind my face too much, that's okay. We'll go to the face because we're not active yet. Hey, Draadstaal is here. Good evening. So I have a Dig Octa V4 running on a 5-volt supply doing some tests. And I have a Dig Uno V4, which was one that still needed to be tested in the new design that's been running on 24 volt for, I don't know, 2 or 3 days. Yeah. Yeah, it's also using the new Quinn ESP32. I should have one somewhere. Do I have one here? Yeah. There. It's pre-stream. We can do anything we want. Let's see. This one. So this will be, am I correct? Yeah, this will be the final design of the new Quinn LED ESP32 board. This is the onboard and external antenna variant because, well, they use the same version, right? So you can see some really small components over there. Hey, and there's a mic there. All boards are getting a mic. Yeah, and it's using the newest ESP32. It's still a normal ESP32, so no S3 or something like that. But with 8 megabytes of flash, so instead of 4, and 2 megabytes of PS RAM. And it has all kinds of extra protections on there, so ESD and voltage, over voltage protection even. The back is less interesting. So, of course, this one doesn't have internet. Yes. No, Ethernet. There's this one, which I broke. That's why it has a red little tapey. This is the Ethernet version. So the Ethernet version is now a single board. So no more double stacked board, because the double stack board, basically, I couldn't get it to pass CE. So the EMI and EMC, especially the EMI, so electromagnetic radiation, or interference, I guess. I couldn't get it to pass because of the double board stack, basically. But this keeps it all on board. It also has a mic. It now uses an external crystal. It has a proper boot delay IC on there, and all kinds of nifty tricks. And, well, this is a fully stacked board. As you can see here, you can see the pins from the Ethernet. So the Ethernet socket here, you can see those on this side, and then the ESP module over here, and then the USB-C is sandwiched with the Ethernet module. And, well, this is the most densely, there's all kinds of little ICs here, which we needed. Very densely packed board, 6 layers, because otherwise it was impossible to route. And, yeah, well, I broke it in testing, but from a test where I expected it to break, so that's okay. And, yeah. Very happy with how this one has been doing. And this one will now pass, oh, can you disable the mic? Well, if you don't configure it, it's not active. I don't have a pickup point, and these are prototypes. They haven't been put into production yet, so yeah, they will have longer pins, so they clear the board a bit better. Yeah, this was a challenge, but came out pretty good in the end. So it was really hard to get this certified. I can tell you most Ethernet boards based on an ESP32 out there are not able to pass certifications. I can guarantee you that. So, yeah. Anyway, hoping to have those available fairly soon. feel this camera is a bit dark. There. Hi there from Hungary. Oh, Slizard is here. Yeah, so no hardware disable for the mic. There is one on the Dig Octa V4. I guess we're sharing secrets now and not after the stream. I don't know. This is a prototype for the Dig Octa V4. So this is the latest one. It has a new expansion header here, which we will be able to do cool stuff with. And it has an onboard microphone here. So this one here, but it has a disabled jumper. So if you take the jumper off, the microphone won't get any power anymore. So yeah, that disables that. And you can disable the SD card over here if you want to, so you can use these extra pins. The pinout somewhat changed, although we're still using the same 16 megabyte flash ESP32 module. This one has an onboard antenna. The actual version will have an external antenna version. But some ports changed, so we're changing this to the Dig Next style, where you have these pluggable connectors, right? So you'll get this cable in the box where you can just plug it in like that, and you'll also get this one for an external relay. There. So you can plug in an external relay and the QEXP connector for some externally broken out GPIO pins. The board still supports 3 independent power supplies, so you can have 5 to 24 volt in here. You can have 5 volt in using USB-C, and you can have 5 to 24 volt in, or 48 volt if you're using the Power 5 HV, using the Q power post over here. And yeah, it's a tightly packed board. It got the output stages of the Dig Next, so it's ESD and over voltage protected now. A fully new custom power stage. Yeah, lots of change. Basically, it's been redesigned fully from the ground up. And we have this expansion header here with which we can do interesting stuff in the future with boards like this one. This is a prototype board. Basically, we can have now, next to having stacked boards on the bottom, we can now also have stacked boards on the top, which slot in like this, and then you'll get some standoffs to make that rigid, basically. And this gives you this gives you 8 output ports in additional to the onboard ports. Now with this Dig Octa, you still only get 8 ports. It's just doubled up, right? Because the ESP32 can't really do 16 ports. But I'm also working on a ESP32, I'm trying to look for it, P4 version. I don't see it. And that will have 8 boards or 8 ports on board, just like the normal Dig Octa. And then if you stack this one on top, it'll have 16 output ports. And what this also enables, if we want to do other stuff like DMX or other functions, we can do that using top boards. So that's going to be interesting in the future. Yeah. Nope, no selectable resistors anymore. This uses the Dig Next circuit. So in theory, those aren't needed anymore for this one. The Dig Quad and the Dig Uno do keep that as basically one of its feature sets, but they have been changed. So we now have a switch for channel LED 1 and 2 and a switch for LED 3 and 4. So I've consolidated the switches. It was also a cost-saving measure, and I needed more space on the board because all components are now on the top and no longer on the bottom, right? So I needed more space for that. So I came up with this. And most people don't need to be able to set it individually per channel. So now you can select it per 2 channels, right? So that remains an explicit feature for the Dig Uno and Dig Quad, but for the Dig Octa, I moved away from it. Because these use a different circuit, which kind of solves that in a different way, right? That's also why you see all these components here per channel. It's also a lot more expensive, but yeah, they solve that in a different way, basically. giving a higher quality output and being less reliant on what type of cable you have connected. Yeah, I'm trying to make them more versatile and update them for 2026. So, yeah. 14 different boards already in the pre-assembled board section on the website. Keuzestress. I need to pick a controller for the LED strips in my van build. Nice. Okay, sure. It looks big. But versus the block that was the forward. Let me check here. Does this one have them? Sure. Okay, so this is the dip switches we had before, and I know it looks smaller, but this is actually also a more expensive solution than this is. So I was able to move these forward a bit, and I could put components around the legs and things like that, which I wasn't able to do with this design. And well, I'll be honest, this board is a lot more expensive than this one to produce. And so that was also a cost-saving measure, right? Without removing the functionality. And I think most people run their boards in 33R mode anyway. So, you know, cost saving a little bit there for something only a few users use. I thought that would be the right step to take, basically. Do you need other stuff for that, or just the same board? What are we talking about? So the V4 consists of a new ESP32 board and new DIG Uno and DIG Quad and DIG Octa boards. So everything's going to V4. Also DIG Octa, although that was still in V2. Hey, you know. We're getting a whole family update with new DC-DC circuits, so it solves that pesky 24-volt issue, microphones everywhere, improved output stages, ESD protection on everything. What else? I don't know. I don't remember from head. Lots of changes. Oh, we're way over time. Why did nobody tell me? We need to go. We'll start. Let's see here. Where is our project? I believe I put it on the desktop. Wall panel sensor. Yeah, so this, okay, so it was a space issue, but because I went to through-hole for the space stuff, but it was also a cost issue. Those dip switches, everything has been exploding in prices. Those dip switches were about 40 cents a piece now, and these switches are about 6 cents a piece. So if on the DIG Quad, that is 12 cents versus 40 cents. So, I mean, yeah, that's a big savings. And on the DIG Octa, it would have been double that. So, yeah. You know, you have to roll with the times. So, those price increases are insane. I've been working on making 5-piece baggies with fuses in there for the most common values we use on the Quinn LED boards. And since most of the things I'm building now is moving to these SMD fuses, right? So the new DIG Quad and DIG Uno will also have these SMD fuses instead of the bigger ATO fuses here. Just to, you know, some improvements again, etc. These, we could get them for a good price. They have been tripled in price just last week. So, but the other fuses too. All fuses we were able to get, and we buy them directly from Little Fuse, have been tripled in price. So we've been selling baggies with 5 pieces, original Little Fuse fuses on the website. Well, now we were selling them for $2.49 on the AllNet store. Yeah, $2.49 is now our cost price. So we'll have to raise those prices and change that. And yeah, I think I'm going to sell them for $3.49. We don't really have to make a big profit on that. It's just insane. But it also means that my production costs for the new Dig Quad, where did I put it? Here. For the new Dig Quad, it just increased by like $2. Just overnight. Just, hello. I don't know. I don't know. I didn't expect the fuse prices to explode, but they did. But my production costs have been exploding left and right since last December. Last December, I got hit like with 20-25% PCB cost increase and 10 or 15% pick and place increase. And then 2 months ago, I got another 25 to 30% for PCB cost increase. 100% increase if you want ENIG, so if you want gold plated. And assembly time has gone up 30%. So, yeah, I'm almost making a loss at these things now. But V4, and that is, I guess, the sad secret, everything V4 and also Dig Next will increase in price once they release. Because the current boards, I'm not sure I'm still making profit. If I am, it's not much. Because they just keep rising. I don't know. They keep increasing the prices on the back end for me, and I don't increase the prices because I hate increasing prices. But I'm hoping with V4 that I can offset the price increases a little bit with better quality, upgraded features. Yeah, I mean, the diffusers contain some copper. I don't know. They didn't give us an explanation why the fuses were suddenly 3 times as expensive. Literally 3 times as expensive. No clue. Zero. We buy thousands of them. It doesn't matter. So yeah, that was kind of sad. Okay, we have our PCB editor. Let's go to the schematics. I'm going to try this full screen layout. You guys have to let me know if that's okay, or we need to make it smaller or remove some stuff from the screen. Or it's not opening. That's always a good start. Uh-oh. Oh, wait. Okay, I opened the wrong version. Hold on. Open with KiCad 10. Is this the correct version of KiCad 10? Yeah, 10.05. Okay. So we go to the schematics. Yeah, that's the wrong window. Let's see. Okay, transparency isn't that bad. We can adjust the transparency a little bit. Filters. Let's give it a little bit more opacity. There. Okay, good. So we've been working on these connectors that are the connectors that are on the back side of the display panel. And we have been working on the PoE circuit. So we have our RJ45 socket we selected. This isn't the one we want yet, I believe. But, oh, I didn't actually research this. Oh, well. Yeah, the increase on, yeah. So we have our RJ45 socket, which then goes, which have built-in magnetics and rectification. That then goes to our PoE circuit over here, which has PoE in and then has 12 volt out. And then from the 12 volt out over here, we have a buck converter to 5 volt. And that 5 volt goes to the board and also to the top board, because the top board takes in 5 volt and then makes its own 3.3 volt there. So the display board. Then from there, we have 2 LDOs we selected. One to make 3.3 volt and one to make 3.3 volt A. That's because I want to have the LDO for the sensor board, which will get 5 and 3.3 volt, on this board. So the heat is further away from the sensors. And then we have, what do we have here? We have 2 relays. Oh, we have 2 relay trigger circuits. that we designed, and then we have the 2 relays we selected. Good. And oh, and over here, let's move this up. Oh, well, we also have a port expander here. I need to start rearranging this at some point. Anyway, we have our connector, and our connector is what will go to the sensor board. And here, we're going to have to make a few changes in a minute. But we'll run through the schematic a little bit more, because we also have a port expander that uses the I2C1 ports. So the same I2C GPIOs or ports as the wall panel sensor. That currently has a few buttons connected and a few relays connected. So that means we can save these pins. That's good. And we have a button circuit here because we reconfigured the port expander, and our buttons have a hardware debounce circuit basically. So that's good. And then we have some terminals for our buttons. So, well, you can connect the wires to the buttons, right? Or switches or whatever you want to use. But I actually figured out we forgot something. And it's good that we still have 4 GPIO pins connected or left, because we're going to need those. And is that including the UART? That is not including the UART. That's good. No, I didn't add anything off stream. I haven't opened the project since we stopped. So I tried to do everything on stream. But we forgot something, or I forgot something, and that is we want to have, or I want to have, millimeter wave sensors, and those need UART communication. So we're going to have the option to have 2. Oh. And thus we need 4 pins for that. And I'm actually thinking of something else. We need even more pins. Uh-oh. Do we have more pins left? Let's see. 37. 2, 3, 4, 5. 2, 3, 4, 5. Okay. Why did I do that in reverse? That makes no sense. Two, because there's very different millimeter wave sensors, and I've seen other boards using 2 to complement each other. I was like, oh, maybe 2 is a good idea. So we're going to use, so 2, 3, 4, and 5 we also can still use, but we might want to connect some random sensors for that. Let's see, 37 we have in use. 38 is over here, 20, 21, 22. 20, 21, 22. Okay, yeah. And then 32, do we have that in use somewhere? Yeah. 46, yeah. Okay, so we still have 47 and 48 if we want to use those, but they are being used for the onboard UART for the ESP32P4 already. So if we can avoid using those, I'd like that. And I'm actually going to remove sensor pin 4 because we need another pin, and that is how's that called again? Something like that. I don't remember the name. Let's see. We're going to call that AW9523B int, because we have buttons on the port expander, which means it's looking for inputs. And what that means is that once a input is triggered on the port expander, the ESP needs to know. Now you can do that in 2 ways. Either the ESP can ask the port expander like 10 times a second, is there a change? Is there a change? Is there a change? Is there a change? That's called polling, and that's okay if there's not too much going on. But the other way around that we can do that is by having the interrupt pin connected to a pin on the ESP32, and then whenever something on the port expander changes, so one of these button states changes, the state of the int pin will also change, which is then connected to the ESP32. And basically, the port expander will tell the ESP32, hey, something changed. It doesn't tell you what changed, but then at least the ESP32 knows, oh, something changed. I will need to ask the port expander what changed. So it's like, ping, something changed. Oh, what changed? Instead of having to ask it 10 times a second while nothing changed, now it knows when something's changed and it'll ask it what changed, right? So that's a lot more efficient. So that is triggering. So with an int pin, you can do triggered changes, and otherwise it's called polling. And polling is the lesser way, basically. So normally this is pooled high, and I believe we need to keep the pool high, but also add this interrupt here. Now this looks ugly as hell. Wait. Let me do it like that. So we keep our 10K pull-up so that the int line by default is high to 3.3 volt. So it's like, on. And then once there is an interrupt, it'll be pulled low, and the ESP32 will sense that and then ask what changed. 10 times more efficient, definitely. Well, the 10 times was just, a random number. I don't know how fast it would pull. Actually, you can probably tell it how fast to pull, because once you push a button, like one of these buttons, which could be connected to a light switch, you don't want it to take 100, 200, or 400 milliseconds, right? So maybe instead of 10 times a second, you'd ask it 100 times a second, so that it only takes 10 milliseconds max before the ESP32, figures out that something changed. But with this interrupt, it's basically instant, because the second this changes, that means this changes immediately, and then the ESP32 will ask, hey, what happened? And it'll register those changes. Okay, so we need this interrupt pin. We forgot that. So we now have that connected over here, and we need these that need to go to our ribbon cable that's going to the sensor board. But we made all these ground connections here, and I already told you we'll probably be rearranging and deleting this at some point. Well, we're doing that now. Sensor pin 4 doesn't exist anymore. We're going to aggregate these, and let's see if we can keep one ground there. I think so. No, I don't think so. Okay. The reason I don't think so is because I need even more pins. Okay. We're going to take this one, and we're going to call this trigger, because those millimeter wave boards also have a function. You can talk to them using UART, right? So it can do all kinds of advanced functions using UART. But the simple way to show that something happened for those is, again, a pin that will either go high or low to very quickly register someone is moving, basically. And then if you want more information, you need to ask it from the UART. But for simple information, it goes through a simple trigger, basically. So we're gonna change this. I'm gonna move this up, and then I'm gonna move this up, and I'm gonna move this up, and I'm gonna move this one there, and then we're going to add these to here. Okay, so we have the millimeter wave triggers, we have the UARTs, and the UARTs go to the ESP32, but these triggers, they don't need to go to the ESP32. We also don't have a lot of GPIOs left. So these will go to our port expander. Let's do it like that. But I need to see, because we reconfigured this with one pulled high. Oh, we didn't use a resistor. Okay, and one pulled low. Sure. Yeah, we can space it out too. That doesn't really matter too much. Sure, we can do that too. Kinda maybe makes more sense. I'm also thinking like traffic on the lines, and these trigger pins are either high or low. They're not going to switch very fast, right? So I don't want them next to, for instance, LED data, which is a very fast switching signal. I'd rather keep them near something quiet. Now, these sensor pins are still doing nothing, basically, right? So these are still open, leftover, whatever we need them for. And we might actually also need to do something with LED data, because currently that is still a 3.3 volt signal and not a 5 volt signal, because we don't have any level shifters. Now we can put the level shifter on this board or on the remote board. I don't know about that yet. Okay. I mean, it's hard to visualize this. I hope that all makes sense. Now we need to look up the documentation for this guy again. Oh. Hold on just a second. There. Because we reconfigured it into a certain mode for the pins. Let me see. For instance, for this one, the boot mode, it doesn't really matter to me. Yeah, okay, the boot mode doesn't really matter to me. Yeah. But we can try and take it into account. Okay. They don't run hot, especially not what we're going to do with it, but there is also a thing about space on the remote board, and anything we can keep on this board, well, we don't need to put on the sensor board. So, and also the signal traveling over the ribbon would already be 5 volt, so that could be beneficial. On the other hand, all the other signals on that ribbon are 3.3 volt, and if we have a 5 volt signal mixed in there, could cause some interference. So I don't know yet. So for this one, we need to check. We have AD0 pulled high and AD1 pulled low. Okay, so we have AD0 pulled high, VBAT, and AD1 pulled low. So that means that these four start up with a 0. So those are off. That's fine, because our buttons are pull high, so it'll be actively pulled high, and then once it senses a 0, it'll activate. That's okay. And then no, wait, I'm reading that wrong. For some reason they start with P1. Right? See over here, and over here this is P0. So that was wrong what I just said. Okay. P0 starts over here, and these are in high Z mode. And that is basically that they're floating, so they don't really care what they are. We're connecting buttons, and those are actively pulled high with an external circuit, so that works. And then we have 4 more ports, which are 0 at startup. So that's where our relays are connected. So our relays are off while starting up. And then we have to connect our wave triggers somewhere. We can do that on the 0 port, and then the millimeter wave sensor would have to trigger high. I think they do. We'll have to look that up. We can ask AI. Do we want to ask AI? Do we have? Right. We're designing with AI, so we're gonna go in Fable Max mode, right? So absolute overkill for Hey, no worries, Medved. I'm asking AI stupid questions. I could just look up myself, but we're we're doing it. We're doing it. While that's searching, we will also look for millimeter waves board. We can also search for it ourselves. So we have, for instance, an LD2420 24 gigahertz millimeter wave radar sensor. While AI is searching, we will figure it out. Okay, so they have the baud rates. Okay, so they have the serial, as I mentioned, serial, and then the presence signal output. Okay, OT1, and let's see what they configure here in the ESP home configuration. LD for presence detection time. Okay, sure. Button. Okay. Number. This configuration is quite complex. Sensor. Moving distance. Okay. Present. Oh, binary sensor. Okay, yeah. Okay. But what kind of sensor is it? Oh, damn it. Let's see if AI has figured it out. Almost all of the common ones are active high. The pin idles low and goes high, 3.3 volt logic, when presence motion is detected. Okay, so that's good to know. Okay, let's go back. So P06 and P07, they are 6 and 7. They start up as 0, so low, and then as Claude, our friend Claude, told us, basically for most MM wave sensors out there, once they sense a trigger, although you can read it from UART, if you're just looking at the pin status, it will trigger that pin high. 6, 7, yes. These are output from the sensor's perspective. Yeah, that's fine. Yeah. The pull down matters because during the radar's own boot, it takes a few. The pin can be undefined or briefly report presence. Yeah, okay, don't care about that. Okay. So now you can put designed with AI on the box. Yes. Okay, so I think, do we want to pull it low manually? I like having defined states. So, wait, did it say that it was pulled low? What did it say? Active high, pin goes idle low and go, okay, yeah. So I think I want to add some resistors. So we want these two. Do we have a 10K resistor somewhere? We should. Let's see, 10K. Yeah, here we go. Okay. We want a 10K resistor. And we want 2 of those. I don't care about this text. And this one goes here. This one goes here. There. Okay, so now we have our 14 and our 13 which are pull downs for the wave triggers. So we know that they'll always have a defined state that is 0. They will be pulled to ground, basically. And then once something is sensed, it'll get pulled high. That is going to travel through our ribbon cable over here into our port expander over here, which will then be fed into this interrupt pin, which is connected to interrupt pins connected to GPO5 over here, which will then travel through this connector to the ESP32P4, which will then be triggered that something changed on the port expander, and then ask over I2C to the port expander, hey buddy, what changed? And it'll tell you, oh, wave 1 was changed from low to high, and then it'll know some motion was triggered from somewhere. And if that sounds way too complicated, that is kind of how circuit design works. I hope that makes sense though, right? So let me move this a bit closer. So where first I was like, I don't know if we need this port expander or not. Well, we have 3 ports that are being used by that. These I2C ports we had anyway, so those don't really count. And a interrupt port now. And we have 1, 2, 3, 4, 5, 6, 7. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we have 8 pins connected to it now. So we would have never had 8 pins left over on our connector to do those things. Well, this is an interrupt system, not a pull. So it's more of a push than a pull. So yeah, we basically used these ports we had anyway to make 8 ports, and we can still even expand even more if we wanted to, because this thing has 16 ports available to it. But where first I didn't know if we needed it. Right now, yeah, we kind of do, because we just put too much stuff on it. Yeah, it's a push mechanism to make it read out the current values. And also where we had this 20-pin connector, and we were like, maybe 16 pins is enough. Well, look here. We have 2 5-volt pins, we have 2 3.3-volt pins, and then we have 1, 2, 3, 4 ground pins left. That's okay. That's fine. And then everything else. Well, these are still free. Okay, so these we can still use for other stuff, but it depends. Maybe there's a sensor on there which doesn't do I2C, so it needs a dedicated trigger pin. Now, those can go either to our port expander, or they can go directly to the ESP32. And it depends on the sensor what it wants. But maybe we decide to put a DS18B20 on there, which is a 1-wire sensor. That would have to go to the ESP32 directly. And maybe some other type of sensor which doesn't use I2C and it isn't compatible with just a high-low signal for the port expander, that would also need to go to the ESP32. So having these 3 pins available still is very flexible, because maybe we might actually want to put a DS18B20 on this base PCB, and then also have one on the sensor PCB. I think that's actually pretty sensible. Those DS18B20s, especially in the TOW92 form factor, they're quite cheap. They're like 10-15 cents if you take a knockoff one. And that's actually an interesting idea. We could put a temperature sensor on this baseboard PCB. So we'd have a temperature sensor for in that wall socket. And then we could put another one on the sensor PCB, basically. Sensible, yeah. Which would be a temperature sensor. And we could potentially use the offset between the two to calibrate something, right? And then, that's only 10 or 20 cents a piece. And I was thinking of having one anyway. This is how feature creep happens. Okay, I'm going to rename a pin here. This is going to be DS18B20. Because I want 2 of these sensors now. I was already going to have one on the sensor board anyway. And you can have multiple on a single bus, right? So you can have a single pin which can have multiple of those connected. So we can have the one on the back PCB we're building right now, and one on the sensor PCB using the same pin. Okay, so that's easy. That only costs us a single pin, and they're much less expensive than I2C temperature sensors. Now, I think we're also going to have an I2C temperature sensors, because I feel like if we have multiple temperature sensors in there, it's not the cheapest way of doing it, but having multiple sources for temperatures, we can, maybe take an average of all of them and then use that as our actual temperature. And that might result in a better temperature sensor than just having a single one on there. Now I'm going to steal this from one of my boards because that means the design time is much less. Let's see here. Let's steal it from the dig quad. One moment, please. It's very easy, so I'll explain it once I've stolen it. Where'd I put it? What? Oh, here it is. Oh, this is a very old schematic. Okay. Clearly not updated this, but that's fine. Yeah, each sensor on the bus has a unique signature or a serial number, and it scans the bus so it knows which serial numbers are on there, and then it can pull those sensors, basically. No, sorry, I meant the sensor board will probably have 1, 2, or 3 different temperature sensors, and then you can take an average of that. Taking an average of this backboard and the sensor board, that probably wouldn't make sense, but yeah. I'm going to delete this resistor because I'm going to take one from here so I know it's the same footprint and stuff. Or capacitor, sorry. So these DS18B20s, I'm using a very cheap one from LCSC because I figured better have a cheap one than none at all. And I've been testing this guy. So the XBLW blah blah blah, they have a few thousand in stock, and if you buy them per like 4,000, and since I'm going to put them on a lot of my boards, I can do that. They're only 13 cents a piece. So, right, because if you only make a few boards, they're a lot more expensive. But for 13 cents, I like to have one on the baseboard and on the sensor board, and then that way we can do some temperature reading. And they're through hole, but that should be okay. And I don't remember. I believe these are 12-bit. Yeah, 12-bit Celsius temperature measurement. If you want Fahrenheit, you can just convert it. That's fine. But each device has a unique 64-bit serial code stored on board. So you can scan the bus and it'll report all the serial numbers it finds. And then, you can, with a single pin, you can still read multiple temperature sensors. And you can even do it fairly fast. And in theory, they're pre-calibrated. They use very little power. They have a good resolution. And yeah. Who wants Fahrenheit? I don't know. You can even use this as a 2-wire device with parasitic power, as they call it. I don't like doing that. I give it 3 pins. That's fine. Yeah. But it's very simple. It's a very simple device, and you can get them for quite cheap. And they're for temperature. I mean, they're not the most accurate, but they're only 13 cents. So anyway, we're gonna use this. So this needs to go. This needs to go. We need to find our. We called it this one. So we need to replace it over here. And we need to place it over here. And then we need the 3.3 volt for the onboard stuff, which is over here. Oh, okay. Schematics are not compatible. There. I'm thinking of having a header socket, but it depends on how much space we're going to have, right? And the idea is that we can support two right now. We'll see once we design the sensor board if that changes or not. This is already out of date. We're going to delete this because this is out of date. There. So now we have the pin connected to the ESP32. We have it connected to this temperature sensor, and we have it connected on our ribbon cable going to the sensor board. And basically the only thing this needs is 3.3 volt. It needs a pull up on the sensor pin, so it pulls down by itself, but it needs, when it communicates, it lowers it. But it needs a pull up for 4.7K, and then between power, it needs a 0.1 UF capacitor for some decoupling, and that's it. Doesn't need any more. That's it. So now we have a temperature sensor on this board, and we can have one on the sensor board, and those, only take up one pin. So now we only have 2 pins left. Okay. We'll see what we use for that. I'm thinking, for instance, we might want to have a PIR sensor on there, a peer sensor, for also movement and presence detection. That's already going to take up a sensor pin. That could go to the port expander, but it's going to take up a sensor pin on our ribbon cable, right? And, well, we have one left. Don't know what we're going to do that we use that for it yet, but we'll see. And yeah, then we still have, we could remove a ground, but at some point, if we keep adding more stuff, we might want to go to like a 24 pin cable, but I don't know. This is what the design phase is for, right? Right now we can still change everything. 24-pin expander and ribbon cable. Well, with the port expander, we now have a lot more ports to play with. If we didn't have the port expander, we would only have these, and then we just run out at some point, right? But, as I said, maybe a PIR sensor, that's fine to go on the port expander. Basically, low-speed traffic, so low up and down, like sensors, those can go on port expanders, but if it actually talks a protocol, like this DS18B20 and stuff, that doesn't work on a port expander, and then you have to have an ESP32 pin directly. Okay. So I think for now, we're going to leave this schematic as it is. I know I still need to do some shell connection here. For now, I'm going to connect this to ground. But I still need to figure out if I need to connect that to... Oh, maybe we can ask AI. Let's do that while we do some other stuff. Okay. Wait, hold on. We're gonna do a new chat. Okay, I have a RJ45 socket. How do I connect the shell? Do I just connect it directly to ground? Fine. Well, AI figures that out for us. we can start on the next part, and that is figuring out all the components, because we now made logical components for everything, but we need to make physical components for that. And we have a button for that called Assign Footprints. And once we hit that, we're going to be we're going to get this whole list, and everything that is currently this, what kind of poop green yellow color, I don't know. We need to assign a footprint. So these, for instance, these are all already assigned, and we need to check those. So it says 0805 over here, and then it means that the footprint should also be 0805. This is what we've called it ourselves. So over this side, and this is the footprint connected to it. So that doesn't have to match. Maybe if I copied something and then renamed it, and I didn't change the footprint, that would have been wrong. We caught some of those last time, right? So let's start here. And now this is a bit complicated because we need a 0.1 UF 100 volt. This is kind of where experience comes in, because I know that needs to be an 0603. I think I'm going to do it differently because it's going to be very difficult otherwise. So this is another view. This is the one with the tables here. And we can see all our values and then which footprints are connected. And for some, I'm just going to add some because, yeah, it's going to be difficult otherwise. Because I know because of the voltage, because of that 100 volt, we need an 0603. And for this one, I think it's the same deal. This one can be 0402. This one probably also needs to be 0603, not connected. C6. Where's our C6? What? So, yeah, the higher the voltage, the larger the package needs to be because of the separation required. Where do we have C6? I don't see it. Save. Oh, over here. Okay. Okay. Yeah, okay. So that's an optional footprint that we didn't put on the board. Okay, fine. 2.2 UF probably needs to be an 0805. This can be an 0603. 0805. Actually, for this... Oh, I didn't put the right name here. Yeah, that needs to be UF. For this, we'll look up, because I don't know for sure. One moment. So we can go to LCSC, and we can say, okay, we want a 4.7 UF, just to go to the right topic here. Okay, let's remove that again. We're going to say, okay, we want a 4.7 microfarad capacitor. And then it says, okay, we have those in 0201 and behind my face. Should I also make my face transparent? No, I'm just going to remove the face for a bit. There. Face is gone. Okay, so it has those in 0201, all kinds of sizes. But if we now say, oh, but I need it to be 100 volt rated. Okay, if we now go back here, we only get 0805, 1206, 1210, 18, whatever. And if I say, okay, 0805 and in stock, oh, we only get 2. And they're 25 cents a piece. This one is 11 cents. Okay, that's better. So let's go back and say, oh, okay, I'll accept 0805 and 1206. That's also fine. Now we have 18. Oh. And then if we say, okay, but I want to sort it. Oh, well, in this case, it's always bad when examples go wrong. In this case, we can see we have an 0805, which is actually the cheapest. Okay. But in 1206, we have many more. No, we don't have many more. Well, okay, this one has a lot more stock. So in this case, it's probably safer to go with a 1206 instead of an 0805 size, so that's a bigger size capacitor. Because of the stock, right? This one has 50,000 and this one has 337,000, while this 0805 one only has 10,000. Okay. But then they quickly become more expensive. So I was wrong. It needs to be a 1206. So this 4.7 UF 1206, but this 2.2, let's also look that up. Wait, where are we? Yeah. So we're going to keep this, but we're going to clear this. 2.2. Okay, apply. 1206, 1206, 1206, 1206. Okay. Really? Yeah, they only have 2 in 0805, and they're pretty expensive. And if we add 1206, they're like a fraction of the costs. Okay, yeah, easy. Okay, yeah. So this needs to be a 1206. So here I you know, because I wasn't verifying it like I should, if we would have taken an 0805 and we would have produced the board like that, that would have costed, I don't know, 20 cents more just for this single capacitor. And that's why you have to optimize your BOM, and that takes a long time, right? So let's do it again. 0.1, I'm pretty sure we can get a an 0603, but let's check it. 100 volt, 37. Okay, if there's like a lot of them available, you're probably fine choosing that variant, right? So you can basically already see from this number, if they only have 2 or 3, it's probably not the right size. So this is fine. The 220 NF, we can check it, but I mean, there. Oh, they only have 4. Okay, let's go to 0805. They have 28. Okay, it needs to be an 0805. Trust it to AI. I don't trust AI to do that because it doesn't do this. This is fine. 2.2. Oh, that's a 16 volt, so that's a lot lower voltage, so that's fine. This is a 50 volt. So here's another choice we need to make. This 0.22 UF only needs 50 volt. This 0.22 UF needs 100 volt. So now we need to make a choice. Do we want to add another component, or do we want to use the same component twice? You don't even see all my movements, right? So do we want to have 2 of the same component, or do we want to have 2 different value components? And it'll depend what is actually more expensive. In this case, I'm going to say we're going to copy this to over here, so it basically becomes the same component. And now we have 3 sharing the same component, so we need less pick and place reels and things like that. Maybe, but then there's just a lot of process involved with this and decision making. You can maybe train it to say, oh, there's only a few of these available. Sure, yeah. 470, that's probably also fine. 0805. Okay, let's check it. 470. Yeah, 0805. Okay, and the rest, I think, no, we didn't do everything. Okay, that can be an 0402. And this needs to be a 1206, I know. Okay, let's save that. And now we can go back to our footprint picker, basically. And now we've added what we think it needs to be. So I'm just going to click here for just easy reference. And now we can say, okay, we named it 0.1 UF 100 volt 0603. So we can just pick this one and that should be fine. It automatically goes to the next line. We name this 0402. We name this, oh, sorry, 0805. Oh, this is 0402, 0805, 0603. I don't care about this one. Sure, we'll give it something. Let's see, 1206. Nope, did it wrong. 1206, 0603, 1206, 0805. There's other ways to do this, but for now we're going to do it this way. 1210, 0402. So there's reasons why certain components need to be some sizes, right? So we can have the same capacitor value, but for different voltages, and that would mean they still might need a different size footprint, and thus also a different capacitor. What? Install any app? Okay, we have this diode here, the PDS3100. I don't know what footprint that needs. PDS3100. We stole that from something. Oh, that needs a power DI5. Okay. Sure. We probably imported that, didn't we? 100 volt 3 amps. Okay. Didn't we import that? Let's see. Do we have a Q import? I'm trying to find a footprint that might match. Why is this so big? It doesn't look like we have the footprint for the PDS3100. We can try and search for it over here. Power... What was it called? Power DI... Oh, okay. I don't know if KiCad knows this footprint. I don't think it knows this footprint. Okay. Does it maybe know the PDS... Why doesn't it know anything? That makes no sense. Oh, okay. Okay. PDS 3100? No. Power. No. Okay, so now we hit a snag. It basically needs a footprint we don't have. So we're going to import that, right? So we're going to use our importer again. We're going to copy this number from LCSC. We're going to go here. We're going to save this. We're going to go to our PCB editor, because that's for some reason where the importer lives. And we're going to use our import GUI. We're going to add that LCSC number over there. We're going to say import, blah, blah, blah. And it imported the power DI, blah, blah, blah. Some 3D models and a mod file, and that's the one we need. So now we can close this again. We can go back here to our assigned footprints. We can go to our PDS3100. And then we can go to our KiCad import, I believe we called it there. And now we have a Power DI that we can use for that. So we can look at the view here. Okay, cool. So we basically stole the LCSC footprint. Now we also need to do that for our ribbon cable that we already imported before. Some screw terminals. We need to determine what kind of screw terminals those need to be. We'll skip that just for a second. Okay, we need to add some resistors. So we can go do it the official way. Let's see, resistor. Yeah, okay. Where is it? Resistor SMD. And this is an 0805, 0402, 0805. And this is the reason I always put the label that I want it to be, or that I've already determined it needs to be, in my description. So I don't have to figure out at this stage what it needs to be, right? I like to determine what size a resistor or a capacitor or whatever already needs to be during the design phase, and not so much during the assigning of footprints. Okay, we need our RJ45 socket, so that's in our import, KiCad import. Oh, there. That's this one. Then we have a QFN19L4. Do we have that over here? Yeah, we do. So these are all we imported during the design already. And then we need our WSON6L2. Okay, we have those. And we need a SOT23.5. Okay, I think we also imported those. So these are all footprints from the LCSC components we selected. So that makes it easy, right? We need a SOT563. Oh, don't have that. Okay. And we need an XFMR. What the hell is that? Okay. So SOT5636 is a pretty standard footprint. We can try and look it up. SOT5636. Oh, it doesn't actually have it. So it does have a SOT563, which kind of looks like, oh, you can see that. It kind of looks like that. But the problem is not every manufacturer uses the exact same footprint. And basically, officially, what you need to do is you need to go into each and every data sheet of every component and figure it out. Well, I don't feel like doing that. So what we're going to do is we're going to go to this LCSC number again. No. There. We're going to look that up. Right, so we need a footprint for this tiny little bugger here. We're going to copy this number because I know LCSC has these for these components, luckily. We're going to go to the PCB again. I'm going to use our import GUI. Yeah, blah, blah, blah. Okay, great. Goodbye. Assign footprints. This guy. And now we have our import thingy here. And we know that one's going to match. And it's probably going to be roughly the same as the one KiCad has. Right? This one has rounded components. So this rounded corners, these footprints from LCSC, you kind of need to treat like good starting points. Because you see that the one from KiCad has like a good keep out and all kinds of data associated with it. And the one we just imported, it has fully square corners and yeah, it's a bit rougher. But, you know, for now, if you're not going to run giant production runs with it, it's probably fine. I often go in and use them as a baseline and optimize for production. So nice rounded corners, changing the paths a little bit. I often do prototype runs, and then I see how the component sits on the pad and how it reflow during soldering. And I often make little adjustments so that if I make a batch of 1,000 or 2,000, it's less likely to have an error than the default footprint, right? If you watch Unexpected Maker, he also does a lot of that because he also does his own production. So it's even closer to the line, basically. Okay, we still need to assign 2 terminals, and those are for the button terminals. I want to use some 3.81 millimeter pluggables. And we're going to use our same method here. We're going to go to LCSC. We're going to go to wire to board, I think. Let's delete that. We need a 1x4 P. We don't have a 1x4. Oh, 1x4. And then we want a 3.1. Oh, no, we don't want that. Sorry. It's always confusing. There, we want a 3.81 millimeter pitch in stock. Let's go. Oh, these are screw terminals. Okay, I didn't want screw terminals. Oh, no, this is a socket. Okay. Sure. What's the difference? Oh, it's a different brand, but basically the same socket. Yeah. It's often, you see a BXDGRC blah 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 and a ZXDGRC blah blah blah. It's basically from Megastar or from Bossy. It's the same thing. Maybe it's a different factory, maybe not. Who knows? It's hard to say. But I know Megastar, for instance, we can use those. That's fine. Nice black connector. Okay. Let's see if they have a footprint for that. Oh, not drawn yet. Damn it. We wanted to steal that one. Let's see if the other one has it. Oh, damn it. Let's sort by price. There. Let's see. Which one can we steal? This one. Oh, the Robo. Yeah, they probably have a footprint for that. No, not drawn yet. Now, I know these, but let's see if we can do it our cheating way. Let's see if we can figure it out. Not many pluggable sockets. I would have expected more. Am I in the wrong section again? No. I don't have a lot. Okay, then we have to do a bit more work. We're going to look at this data sheet here. First off, we're going to select one in KiCad, and we're going to do we're going to go scroll through these. This is all wrong. So I search for 3.81 millimeter because I know that's the pitch of the socket I want. And then we want this style socket over here. So we have 4 pins and this sticks out. And this is a Phoenix contact one. Let's see if KiCad already has a different one. No. Not really. Now I know where you can get some different libraries which would have them, but for now we're just going to take this one. The only thing I need to verify, I can't verify over here it seems, is, okay, during PCB design we'll need to verify that these holes are the correct size and spacing for what they've drawn in the datasheet for the component we might end up selecting. And here you can see that they want 1.4 millimeter drill holes, and what I often see from the KiCad footprint, yeah, I can't really measure that over here, I think. Anyway, I think these holes are probably too small. So we'll have to adjust that, and then we have a fairly good footprint we can use. But if there's not a footprint you can find, you can download, you'll have to make them yourself. And you used to have to do that a lot more. I have a lot of custom footprints. But yeah, that's a lot of work, right? Then we're going to spend another few weeks making footprints. So for now, we're going to use this, but we need to add a note. Let's add a note in our check PCB holes and footprint. There. We're going to add a note. And then we're going to assign this the LCSC number, because we've been doing that. Where is our... So we said, okay, we're going to use this one. LCSC. Okay. So on my boards, I have custom footprints for all of this stuff, which has been formed over the years and doing lots of prototypes and adjusting footprints to make them solder better and things like that. Right. So we need to make sure we do this. Oh, wait, we were waiting on AI to give us a answer how we should connect our shell. Let's see here. Where's our AI? Our AI is here. No, not directly. With the board in plastic enclosure, no protective earth, an isolated blah 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 stage, the shell needs to be treated as its own chassis node, not digital ground. Both shield eggs go into a small copper island chassis, voided from every plane underneath. No ground or copper under the island or... Okay. It's very hard. It really depends on the exact product you might be picking, and then I just adjust it yourself. So, yeah. Bridge that island to digital ground at exactly 1 point with a 1 NF and 2 kilovolt capacitor in parallel with 1 mega ohm placed right at the jack. Keep 2 millimeter clearance between the island and all copper, consistent with the isolation mode on a... Okay, yeah. Blah, 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 blah. Okay, that I kind of know what to do there. So we need to fix this. I figured this wasn't allowed, but you know, you can try. I'm going to connect this together. And then we're going to add some stuff here. I already said with cap, but we need a capacitor and a resistor. So I'm just going to steal something over here. And we're going to change that to a... Oh, actually, we're going to look it up. What did it say? We need a 1 NF capacitor and a... Oh, for 2 kilovolt capacitor, yeah. And a 1 mega ohm resistor. Okay. 1 NF. Okay. I think this needs to be a 1206, but we're going to look that up. This is incorrect. Okay. So let's look that up. We want a 1 NF. Oh. No. Ceramic capacitor. So we're going to do the same thing again. We're going to say, okay, we want 1 nanofarad. Yeah, and then we want 2000 volts. 2 kilovolts there. We don't mind. It's okay if we can do more. So we're going to say up to 6. I don't know. With 10 kilovolt, that's fine. In stock, apply. And then we're just going to sort it to the cheapest. Okay, this has 259,000 available, and that's a 1206. Sure. So we can select this. That makes it easier in the future. Let's see. LCSC is this. It needs to be a 1206. 1206. Yeah. Okay. So this is our capacitor. and that needs to go to ground. And then we also need a 1 million ohm resistor. So I'm just going to look up 10K real quick because I want a surface mount. Okay, go away. We're going to say we need a 1 mega ohm resistor, which again needs to do 2 kilovolt or higher. Okay, we only get a few. Oh, that's a 1210, damn. 2512, okay. That's expensive. Oh, okay, yeah, that's fine. Oh, wow. Why is it so expensive? Bridge Island, 2 kilovolt, a pair of 1 mega ohm. Two packages. Cap should be 1206 or 1808. We use the 1206. Okay. And the bleeder should be 1206 anti-surge during... Yeah, okay. Okay. So we're just, I wanted 1206. So it doesn't need to support 2 kilovolt continuous. It just needs to survive a surge. Basically, we're going to choose the type of capacitor we want, or a resistor we want. A thick film can generally survive a surge, where a thin film can't. So we want a thick film capacitor, and we want a 1206. And let's say 1 kilovolt or 800. Let's see. Okay, now we get some results. Yeah, probably one of these is fine, but let's see if the AI can find a better one. Sure, give me some good LCC numbers for the resistor. Let's see what it comes back with. Oh, it uses our connection, our MCP, so that's good. Reconsidering strategy. Oh, search strategy. Okay. Yeah, it can't really search for anti-surge because that's not something LCC lists. So you actually have to dive into the data sheets. We'll see what it comes back with. Probably one of these. This one has 120,000, so that's probably a good pick. We can go with that, but because it's a surge, so it doesn't have to have a continuous rating. Deciphering. It's still searching. Still searching. Now I get a break again. Oh. Using the most advanced AI on the planet to find our resistor. Because that's what you do, right? You need to use the most advanced AI on the planet to find the right resistor. But now we have a choice. We have a choice. Do we drink the cherry vanilla flavor or the cream soda flavor? You guys get to pick. You have 10 seconds to respond. So, cherry vanilla flavor or cream soda flavor? And the first response is cream soda from Drastal. Okay, thank you. Well, during this quiz, our AI didn't finish. Okay, so there's 3 cream sodas and 1 cherry. Sorry, cherry lost. Sorry. So, okay. Our max intelligence AI. You got one cooling now. Nice. I like these. I'm more of a Coca-Cola fan, but these Pepsis are pretty good. Oh, it's doing stock checks now. Okay. Okay. Maybe it's going to get something. Maybe. Curating verified resistor options with optimal availability. Yes! I can sit back and relax, do nothing. Oh, there we go. Okay, so both leads verified live. Here's the shortlist. Not every anti-search type is an extended part. Oh, okay, cool. So they've included the 0 fee workaround at the end. What? This is okay. Well, I don't care about extended parts. I'm not gonna, you know. So we have a Panasonic blah. Okay, it's 2 cents. That's fine. Is this in 1206? I don't know. And we have the Uniroyal. I use a lot of Uniroyal stuff. So anti-search, high power, half a watt. Okay, 4 times cheaper. Yeah, that's fine. Okay, so it found some more. Sure. What you're actually buying with these isn't the wattage. The bleeder dissipates microwatts. It's the element construction. Anti-search parts use a wide trim pattern without the sharp laser notch. Blah, blah. That's all true. Good information. The economics alternative. Every part above costs you extended feeder fee. I don't care about that because once I assemble these PCB, I have a feeder cost anyway. So that's fine. That's why you want to assemble 1,000 boards and not 2. 2 standard blah 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 in series gives 400 volt working and 800 volt overload across the pair, split into impulse, no fee. Totally fine. Yeah, blah. Okay, sure. So we're going to look up this one. So this is a 1206, 1 mega ohm. Is it indeed a thick film? Yeah, that's a thick film resistor. Oh, it's a 200 volt rated part. Okay, that's fine. Okay, so anyway, we're going to use this one. Cool. So yeah, you can use AI to look up parts, but I mean, it took a while. It burned through like a wad of cash doing that. I don't know. Sometimes it's useful, sometimes it's not really. So this is 1 mega ohm, 200 volt, 1206, and we need to do a 1206. And then we need to have some LCSC number here, so we don't have to look that up during assembly. And it needs to be in parallel. Something like this. I usually do it like this. So this also needs to go to ground. And it needs to be in parallel, so like that. And with that, this is solved. And our shell is now connected with this resistor and capacitor to ground. Which should be the correct termination for that. Okay. We can actually ask it. So I'm now wondering, do we connect it to ground or do we connect it to PW0? I think we connect it to ground. But I haven't done too much PoE stuff. Do we connect it to ground or PW0 on the socket? So we just ask it. Untangling isolated power architecture grounding considerations. Whoa. How long did it need to think about that sentence? I think it needs to go to ground, I'm pretty sure. But, you know, we can ask. We can ask. Great sound effects. Thanks. Reconciling primary and secondary ground domains. Oh, weighing ESD current paths through digital versus primary ground. Whoa, it's asking so much stuff. Okay, we're going to go back here for now. We'll wait for that. So I think this schematic is now basically done. But if you can remember where we started with this block, and then we started building this block, and we needed these power conversions, and then we added these relay triggers, right? Relay trigger blocks, and then we added a port expander and some button inputs and terminals and a temperature sensor and a ribbon cable to go to the other board. Some resistors here. That is a lot. Oh, we need more resistors. I forgot. Oh, damn it. Damn it. Damn it. Normally I don't put I2C resistors on a board because those add-on boards generally have them. But we're going to use I2C. But this is the onboard I2C. So this is the I2C that is already on the ESP32 wall panel itself, right? So I would assume those already have pull-up resistors because they use I2C devices on the wall panel sensor itself. So let's look that up. Wave share, blah, blah, blah. Okay, let's go here. So we're using this this little thingy here. So I believe they already use some I2C devices, and we're going to use those same pins for the ones that are on this board. The ones that are on the sensor board will have their own I2C network. But for instance, this capacitive point touch tracker seemingly already uses I2C. Oh, I didn't actually know that. 7 and 8. And then their audio codec uses I2C. And their microphones use I2C. So I would imagine it already has pull-up resistors. But let's check the schematics. Schematics, where are you? This is the wrong page, I guess. A wiki? Do we need to go to some kind of wiki? Resources. Oh, okay. Schematics, okay. Okay, that's pretty good. Oh, we might be able to use this as dimensions later on. Anyway, so let's see here. Can we find some I2C pull-up resistors? Micro SD card, the C6, okay. Some power stuff. No. USB to UART, no. Interface. Oh, maybe we can search for this net. ESP I2C. Okay. Okay, so they have an ESP I2C SCL. Okay, this is a weird net, but fine. Let's trace those. Okay. Here it has some capacitors. Okay. Why? Sure. Okay, here's ESP32. I can't zoom in more, sorry. ESP32 3v3. And that has two 2.2K capacitors pooling ESP I2C SCL and SDA up to 3.3 volt. Okay, so that verifies that they have pull-up resistors on the I2C lines already. So that means we don't have to have those. Okay, now on our design, we have designated a second I2C bus, this guy here, which will live on the sensor board only, because otherwise I feared we would stretch the traces too far, basically. And for those, we do need pull-up resistors, but I think we'll do those on the remote board because of how the signaling works and stuff like that, right? So, okay. So we don't need extra pull-up resistors for I2C. I'm going to make a note of that. Note ESP I2C has pull-up resistors on TFT board. Sure, whatever. There. We were asking AI something. AI. Oh, it needs to go to PW. And this supersedes the bridge to digital ground from the earlier in this design. That recipe is right for non-isolated boards. Blah, blah, blah. Where digital ground is the only blah, blah. The logic, with a flyback isolate, your board has two domains. The line domain pairs MagJack PW plus, okay? And the secondary domain, digital ground, yeah, okay? The shell belongs to the line domain because everything it interacts with, cable shield pair. Okay, so, okay, the Bob Smith, yeah. Strike hit shell, 1NF, PW0, through the rectifier diodes, line center, okay. EMC, okay. Practically, shield tabs, chassis island as before. Then, islands as before, yeah. Then the one NF and the one mega ohm to the PW. Okay. Yeah, I know. I don't care about that. Okay, so we did it wrong. This does not go to ground. It's good that we checked. I actually didn't know. So this goes to here. Okay, as I said, I haven't done too much with PUE yet. So this is our PW minus and PW plus. That's the rectifiers, in this case, in the socket. And our ESD protection needs to go to there instead of to the digital ground. Okay. Now I'm wondering about this ground, but I think this needs to be our normal ground because that's after the rectifier and not before the rectifier. The shield basically sits before the rectifier because that's on the cable side, and then this ground basically sits after the rectifier, right? So it's just a person in India Googling your question while being underpaid. Okay, so now we figured this out. Good. And we have all this done. I think it's time. I think we're finally going to hit the PCB button and see our PCB. Well, no, actually, we won't see our PCB yet. We're hitting the PCB button. Okay? Here is our PCB. There's nothing there. So the first thing you want to do is actually draw the PCB outline, but we have to figure that out. But what we're going to do, we're going to go one step ahead, and we're going to hit this button over here, update PCB from schematics, and then it's going to pop up like, oh, wait, you need to annotate and blah, 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 and update it, and it's going to add all these components that we just gave a footprint, right, a physical print. Okay, so we're just going to say, okay, sure, update PCB. Bam. And this is all the components we need to put on this PCB somehow. And, well, yeah, that's what we need to do. Okay, let's, I don't know, for funsies, measure this. Where's my measurement tool? Oh god, this is KiCad 10, isn't it? I used to have a measurement tool. I don't know where it is. What do you mean? Why can't I measure anything? Add barcode? No. Huh. I'm so confused. Yeah, they do that on footprints to designate pin number 1. So this is pin 1, and then these are the other pins, basically. But you can see that on some other footprints too. They'll either have a dot. So this one here has this dot over here. So that notates where pin 1 is. This one doesn't care because you can't really do it in reverse. This one here, pin 1, has a dot. Here we go. Pin 1 as a triangle, so an arrow. Here we see again these connectors. Pin 1 is a square, and then these are all round. So it's it's to designate what pin 1 is, right? So you don't turn it around. It's on the left now. It is? Okay. Millimeters? Inches? No. Okay. Tools, measurement? I don't know. Where's my ruler? What's going on? Measure tool. Yeah, here we go. Why is it gone? Weird. Anyway, I just wanted for fun to do this. Currently, this is taking up about... Oh, okay. The font is really small. Sorry. 55 millimeters by 57. Okay. 55 by 57. Okay. So, how big is this screen? Right? This little screen here? I don't know. We can measure this PCB. Because we can make it roughly the same size, right? We can't really make it bigger. We probably actually need to make it smaller, but that's another discussion. So let's take a look at how large the original PCB is. It's probably, yeah. So this is about, oh, sorry. This is about 8 centimeters, let's say 7.5 by, that's actually a bit smaller this way, by 7. Okay. Now, I think we'll probably be able to make it fit, but we'll see. I want to try and avoid having dual-sided components, so having components on the back and the front, because that means you have to do double pick and place, which is basically, it's not double the cost, but it adds a lot of cost. Now I'm going to disable some layers here. I'm going to disable the fab layer because that always throws in lots of nonsense. Yeah. So these are our SSRs. This is our RJ45 socket, and then we have our Ethernet, I think. Oh no, this is our port expander. Now what we can do, because I'd like to separate this a little bit, because I don't know what this capacitor or resistor belongs to, right? It's totally random, but they do belong to stuff. If we go back to our sheet and we just select all of this, okay, we just select that, and we go back to our PCB editor, and we now hit M for move, it basically also selects everything we just selected in the schematics editor. And what I like to do is I like to, you know, pull it apart into blocks we also made over here, to basically be able to, yeah, organize it a little bit, so I know what belongs where. Okay, so this is our PUE section. And then after our PUE section, we're going to get our buck converter. Our buck converter is really small, so that's nice. So this is our buck converter. Then we have some LDOs. So let's pull those out. Those aren't too big either, just some capacitors and the LDOs. So I'm going to put those below here. And let's do our port expander. Just going to put those together and put them down here. Let's see what else. Okay, our button pins. There's actually something we need to add. I forgot again. These button pins don't have ESD protection. And since they could be in boxes with other stuff in there and things like that, we might want to add some ESD protection. Let's make a note for that. We're not going to do that today. So, okay. We have our temperature sensor. As you can see, that's just, you know, a resistor, capacitor, and the sensor itself. It's not that big. Easy to integrate. Then we have our button terminals. Oh, I guess those go with the buttons over here. We have our FPC connector. That's going to be the connector that goes to the other board. We have our two input connectors from our top board. And then we have we have our two pull-up resistors. From our trigger pins. Yeah. So those can go with our I2C expander, actually. Those can go here, right? Okay. Okay, so we separated it a little bit. We can take a 3D viewer look, because I think most stuff will have footprints. Oh, what are these? Did we have to... Oh, those are our relay terminals, I think. We might also want to make those pluggable. I don't know yet. We'll have to see. We don't have any footprints for these, it seems, or no 3D models. We don't... Yeah. We probably still need to assign some 3D models. Wow, look at that footprint. Fancy. Okay. Okay, yeah, we're missing all the imported stuff. Probably doesn't have a 3D footprint yet because we still need to assign those. Yeah, if you want to know everything that goes together, I just go to the schematics and select it like that, and then it automatically shows it, selects it in the PCB editor. It also works the other way. If you find like a random resistor over here, and now we go back to our schematic, it says, oh, that's this resistor, right? So that's all linked together. And normally when I'm editing, I have two screens. So I have the schematic open in one and the PCB editor open in the second. And often I have the 3D view open in the third one. And then I can basically manipulate anything anywhere. And I can see all the relations at the same time, right? So that helps a lot in efficiency, I guess. Okay. How long have I been going? 2 hours and 8 minutes. Okay. So, I think the first thing we're going to do, and it's also going to be the last thing today, is draw an outline of the size we want to make our PCB. We just measured that it's about 8 by 7 centimeters for their version, basically, right? But the most important part is that this connector needs to be in the right spot, because that needs to connect to their PCB. And then we might also want to make holes for their there's these the screw terminals over here. Our PCB probably wants to screw into their PCB. 6, 7. Oh my god. So actually, we'll start with that. First, we'll see if they actually have documentation, because I actually don't know. Drawing. What does that mean? PDF? Okay. Yeah, 86, 72. Okay, they have a drawing for the screw holes. So that's good. These are 70 by 74, the screw holes. Oh, wait, I'm not sharing the screen. Sorry. So they have this drawing. This is whatever. But the screw holes are 74 millimeters by 70 millimeters. And then they also show it in relation to the chassis. And they show, oh, this is good. They show the relation of this header socket in relation to this screw hole. So we can match that up, and then we can be pretty sure we'll be able to align whatever size PCB we make using the 4 screw holes and this socket, right? Because this socket, we need to align this socket. That's the most important thing. But this is basically all the measurements we need, because we just need to make sure we can mount these screw holes to their PCB. Theirs to ours, we'll have to use some standoffs or something like that. And then this socket, and we now have all the measurements. Let's save this to be sure. Yeah, that's perfect. I want to rotate this. Can we rotate this? Yes. Wait. No. Oh. What? There. No. Still wrong. Okay. That's better. So the top ones are 70 millimeters and these are 74. So, okay, let's do that as the last thing for today. Let's see how we're going to do that. I wonder what size screw these are. I'm thinking M3. Do I have some? I have some M3 screws here. Let's give that a try. Right, because we want to use these. This is an M3 screw. I'm not sure if it's the right thread, but we'll see. These aren't magnetic, so what? Oh, okay. Okay. And this doesn't feel the right size. Okay, this feels too big. Let me see. I have a standoff here, but I think this standoff is also M3. Yeah, that doesn't fit. Let me see if I have a different one here. I do. So this is M3, I think. This one. So this is probably M2.5. Is it even smaller? Yeah, it's even smaller, huh? Okay. Let me get a box. Hold on. Do I have a stand-up box for that? So I have some more M2.5 here. Let's give that a try just to be sure. But I'm thinking it might need to be M2. I need to think about where I have M2s. Yeah, this is also too big, so M2.5 is also too big. Let me see. Let me see. I have my box here. But in theory, this is all M2.5. M2.5. Nope. Two point five. I generally try not to go below M2.5, so I can check what's in here. This might be smaller stuff. Oh yeah, this is smaller for sure. Okay. What's this? I don't know. It's a very nondescript label. This has been closed too long. Okay. That kind of works. The ring is in the way. Yeah, I mean, that's in there. So that's good. So I'll have to order whatever this is. Let's see if we can figure that out. I think this is M2. Oh, maybe I don't have to order because I have a lot of stuff. Right? We already have like 47 millimeter. 40. Why are you not focusing at all? 43 millimeter, 47 millimeter. Well, this is much longer. Let's see what this is. 45. This is probably 45 millimeter, and this is this 50 millimeter? No. Let me measure that. No, this is 1 centimeter. Right? This is exactly 1 centimeter. And it's from the 050 bag. So that makes perfect sense. Okay. And then we have lots of little screws. But I don't know what size this is. I'm thinking this is M2. So what I'll do if I have to see if I can get that in before next time. Don't know. Let's put this all back. You can buy kits like this, right? Yeah, I can look up the part numbers, but you can buy kits like this, and I'll buy a kit with M2 and M1.5, and I'll try and look up what this is. And then we should have various lengths with which we can then figure out what we need, because we need the right standoff for having a PCB on these standoffs and then a screw into the PCB. So this mounts together as one unit basically, right? But it needs to have the exact right height for this connector and the connector on our PCB to mate together perfectly, and then screw it down so that it's screwed down as one whole. That's basically the idea, right? And then we still need to figure out how we're going to mount that, because the mounting into the wall socket will probably have to be on the PCB we make, because it sits behind this one, versus on, because this has no mounts, right? This is just a box. It doesn't mount to anything. So we'll have to make our PCB screw into those 4 holes and mount this connector. And then our PCB needs to mount into the box and hold it against the wall. Somehow. I'm not quite sure how we're going to do that yet. It might require a third PCB, because the way they did it is they have this back panel with this plastic enclosure with this thing in there, right? So this mounts to this, that mounts together with that connector, and this basically snaps in here, I believe, somehow. And then they have some screw holes there and there with which you mount it to the wall, and then basically you click this on there. Yeah. I have no idea how we're going to do that yet. I might need you guys' help for that, because, yeah. That's going to be interesting. It doesn't have a dedicated section on Discord yet. Might actually be a good idea. But there is now 7 videos, I believe, in this WPS project. And it's basically to make an expansion board for this wall panel sensor, or for this wall panel, to make it into a wall panel sensor. First, we're going to make a baseboard where it mounts to, where we then have some sensors and other electronics to make it PoE compatible. And then there's going to be a second board we connect to that, which will have all kinds of sensors and things like that on there. So we're basically going to make an expansion board for this thing. Okay, so it's probably M2. Okay. Whoa. Interesting. Hold on. 1 second, please. There. Okay. So what we're going to do as one of the last things today, I think, is we now know that we need at least 4 screw mounts. So we're going to go back to our schematics editor. We're going to say I want a new footprint, and then I want a, how do you call it, mounting hole? Yeah, mounting hole with or without pad. Do we want to transfer ground? No, because these are not grounded, I think. These ground? No, these are just plastic inserts. Okay, Okay, so we don't need one with a connection. We can use the one without connection. There. And we want 1, 2, 3, 4. R2D in the back. What? And we're going to assign a footprint, because these now don't have a footprint. And we can say mounting hole. Need to empty this. And we just determined that it's M2. And if you look at the M2 holes, you can just have a normal hole, or you can have a different one, or one with copper around it. What I like to use is this one, because it has some vias in there, and that basically makes it a bit stronger. So we're going to use the M2 with via pads, and I know it then has enough spacing also for the screw head and things like that. So we're going to do that 4 times. There we go. Okay. And then we're going to go back to the PCB. We're going to import changes. Okay. And now we have 4 mounting holes. So we just looked at the drawing here, and we saw that these center of the mounting holes are 70 millimeters apart. Okay, so now we're going to do some more complicated things. We're going to take this one. We're going to put it on the same plane. Oh, okay. Now we're going to change the setting. We're going to go to Preferences, Display Options, and then we're going to say Full Window Crosshair. Because now I have a full window crosshair, as you can see, and I can put it over this hole, and I can see the lines with the other one. So I always have that enabled. Okay, so let's go here. And this mounting hole is on 1/6 blah, blah, blah. We're going to put it on 115 and 28. Okay. There. It's now over here. That means that if this one is on 115, and we need, okay, we need to add 70 millimeters. So, okay, we're going to say 115 plus 70. That is 185. So we're going to go to this one. This needs to be 185, and this needs to be 28. So now this is 70 millimeters apart if I have my measuring tool. Measure tool. We can say the middle of this one to the middle of this one is exactly 70 millimeters. Okay, that makes sense. Then we're going to take this one. No, okay, I need to know this number. 115. This one, okay, it needs to be on 115. There. But this one starts at 28. And we go back to our drawing. It says 74 millimeters from this one to that one over here. So, what was it? 28. We take our calculator. I don't remember. 74. Plus 74, that is 102. That means we edit this one. And we say, 102. There. So now this one is also in the right spot. Right? And then we can take our last one. Move. It's about this, but we can just find the numbers. We can edit this one. It needs to be 185. Edit 185. Okay. And we can check the other number over here. 102. 102. Okay, so now we know that our screw terminals, or our screw mounting holes are all in the exact same position as theirs, basically, right? 74 and 70. So what we can do now is we can take this box drawing tool over here, draw a rectangle. Sorry, we need to do something else first. Over here, we click on edge cuts. So we are on the edge cuts layer. Then we take our box and we put them right over the screw holes. And we basically go to the other one over here. And we click now, and now in theory we have a PCB that is the exact same size. Yes, the connector should be able to be placed with the offsets as well. If we now look in our 3D viewer, because we did the edge cuts layer, it knows our PCB needs to be that size. We basically just told it we want a PCB of this size. So now we have this PCB floating here, and we have our components floating over here, and we can start putting those together. But now we at least know the right size for the PCB, and we probably want to do this slightly differently. I don't know if they have a function for that nowadays. Can I select this? Why can't I? Oh, there. Because I want rounded corners. Rounded rectangle. Oh, nice. Oh, look at that. Okay, they have a function for that now. Because I'd like a bit more round corners. Okay, that's pretty good. That's pretty good. Let's see if we go 3mm. Oh, okay, that's a bit too much. 2.75. Yeah, almost. Look at that. Look at that. Perfect. So now if we look in our 3D viewer, we'll see that it's rounded off. And it still has a little bit of meat, right? So it's not intersecting with the screw terminal itself. Or the screw terminal, the screw hole. And where are we? There. Perfect. Look at that. So now we have a nicely rounded PCB. I always like that better than just those square edges. And nowadays it doesn't cost too much. So, okay, perfect. We did have these connectors, right? But I'm not sure we selected the right ones. We can try and do that today. I might move it to next time. Let's see. LCSC. Did we select the ones we need already? Yes. Okay, we went with through hole. That's fine. But I need to think about these. Need to go on the bottom. Do you want 2 to 5mm around holes? I'm not sure what you mean. Basically, the type of footprint we selected already has this around the hole, which the screw head will land on, basically. So the hole is M2, but this footprint itself is already larger. Yeah, that's fine. I'd rather make the PCB smaller than bigger. So, I might actually, in the end, make this even smaller and then just have little legs with these screw holes on there. But we'll need to see if we can fit it all on there. I think so. But, yeah. So we want to use these 2mm spaced. Did we select 2mm spaced? Let me check. Yes. Okay, good. But these don't go on the front. Because if we now look in the 3D viewer, let's deselect them, they stick out over here. But because we need to mate this PCB with the one that's underneath it, and that has irritating disk, that has these pin sockets, this needs to go on the bottom of the board, right? Because they need to stick out on the bottom of the board. There's some other methods you can use, but what we're going to do is we're going to select them, and we're going to go to F front copper, and we're going to say F. And what F does is it changes between the front and the back layer, basically. So if we now look in the 3D viewer, we now see that we have these solder joints because the actual connectors are now on the bottom, right? I hope that makes sense. And we're going to rotate them. And basically butt them up like that, because these have a... Oh, where's my measurement tool? Irritating. These have a 2mm spacing. Sorry, I can't make that bigger. They have a 2mm spacing, so let's see how far this is. These now have a 2.5mm spacing. I don't want that, so I'm going to move these over one. So now they have a 2mm spacing again, and then in the 3D viewer we need to see... So this is now all evenly spaced, but we can check with the footprint if that's actually possible. Yeah, it looks like this is now perfectly aligned, and there's no space between there, and that should fit, right? I mean, it also fits on their board, so yeah. We basically need to mimic that. Did they leave some extra room there? I don't know. I need to get the calipers out at some point. But if I look at that, I think that whole spacing is basically even. Right? Also, the leg spacing of the solder joints also looks even to me. There's no extra space there. Or at least not a lot. Right? So even if I take... where is it? No. Where's that other board? I just had it. Oh, here it is. So let's take this other board, right? Let's take their board, which has this connector on there, and let's insert it in the middle. So basically, let's insert it like this. Okay, so if we do it on one side, it goes in, but if we insert it offset, yeah, it still goes in. Even if there's a difference, it's not much. Right? Let's try another offset. Yeah. It's a bit more snug. But I'd say that basically fits. Right? So we can do the left position. Or we can do the right position. But we can also do the middle position, basically. It's a bit more snug. But it's not like it's one space over or something like that. Because the pins also aren't bent. Okay, so we're going to leave that like that for now. We'll have to see on the first prototype how it looks. I don't know. Okay, so that's good. So now comes the more difficult part. Let's see what their drawing says. They say that this middle... Okay, let's do this first. The middle of this connector is at 16,64. So we need to know... Edit. this 28 16,64. Oh, what? 44.64. Okay, so then in theory I can say 44. Yeah, I think so. Let me just do this manually. 44. Yeah, you can say right click, and so you can select them both, and then you can say group. You can group them together. Oh god, you can't see anything. Sorry. You can group them together with grouping here, but I don't often use that. Sorry about that. Yeah. So what we did is we took the number from here, the 28, and we added we made it go to this position. So in theory, yeah, this doesn't have the screw holes. So in theory, this is now in the right spot. I can put it here. So, except that we still need to align it. What did they say about that? So the middle here should be 14.07. Wow. Okay. Let me draw a line which starts here and needs to be 14.07. Let me just make that. So we're making a line. We're starting at 115, and we're adding 14.07. So it needs to end at 129.07. So this line, the end of the line here, is now in the correct position for being exactly in the middle. Right? So that's what this drawing says. Middle of the screw hole ends in the middle of over here. Okay? Sure. Which is 2907. Okay. Problem is I can't really do that, because once I move in this position. Oh god, I don't want to move it. How do I do that? Yeah, so the only way I know how to do that is basically I'm going to draw a line. And I'm going to draw that line to underneath it. And I'm going to take these two. I'm going to set my grid to very low. And then we're going to move it with the arrow keys until this is right in the middle. And then we're going to measure it, if that is indeed the middle. So this is 1 millimeter. And this is also 1 millimeter. There might be a better way of doing this. And they're 2 millimeters spaced, by the way. There might be a better way of doing this. I don't know. But this is the way I did it. Let's save that real quick. There. Yeah, we can also make another one over here. I really don't know this measurement. Hold on. Let me see. This is the middle about. Yeah. This should be 16.64. I didn't pay attention. Okay. No, again. Wait, I need to use a different tool. 16. 6.5 at least. Yeah, now I can't see it. 16.64. Oh, okay, it's actually wrong. And this is... Okay, I actually did it wrong, because you can see that the 16.64 is to the middle of these holes, and I thought it was to the middle of the footprint, but their 16.64 is to the middle of the footprint, not to the middle of this hole, which doesn't really make sense, but okay, that's how they did it. So we now need to take these two, and we need to move them up until this is in the middle. And we kind of need to do this visually because we don't have the right measurement. Let me see. Yeah, this all lines up now. 16.64 from the middle of the screw terminal. Yeah, that looks good. Okay. Okay. So in theory, this is now all lined up. Now, one thing I didn't do, which is kind of stupid, is I didn't check which one is which. I think it's probably wrong. Is this the left one or the right one? This is the right one. Yeah. Yeah, I know that this board is the Ethernet board. So this one is the Ethernet board, and it only has one connector. And it connects to the right one. But we need to think in 3 dimensions. But if this is connecting to the right one, ours is also, we're going to connect to both, but we're going to connect top down. And we're looking at our PCB top down. So these are in reverse because the Ethernet pins are here. Oh God. Our Ethernet pins are here. And our power pins are here. But on the board, it's actually reversed. So I think we can solve that pretty easily. 11607. One moment. And the other one is 13007. So this becomes 11607. And that was, which one was it? No, I need the Ethernet one. Yeah, and this one then becomes 13007. Okay, that's good. I hope that made sense for everyone. Yeah, so now, if we look at the 3D viewer, these should now be in the correct spot. And I think if we compare that to... oh, you can actually try and line it up. Let me adjust the opacity here. Of course, this is non-scientific whatsoever, but we have the screw hole there. It kind of lines up. Noise. Oh, noise. Yeah. It kind of lines up. I think it lines up. It's non-scientific as can be, but we could make it line up, so it's fine. Okay. Yeah? Well, that's why you make prototypes, right? We're going to have to prototype this. Cool. So yeah, we made our first PCB, or well, you know. And then once this is, we produce this PCB, we need to figure out the standoff distance, because our PCB, it has a certain thickness. It's probably going to be 1.6 millimeters. But then this connector here has this little plasticky part here. But this one also has the plasticky part. And that all needs to mate together, so it's nicely secure. And then we kind of need to figure out the distance and then the right standoffs for that. But I'll order a standoff kit at least, so that we can figure out if it's M2, I think so. And then we can find the right height for the standoff. This might actually be pretty okay. Yeah, because their own PCBs, they're actually not screwed in. Look at, I mean, there's no screw holes in this. There is screw holes, but they don't line up, if anything, because it mates into their PCB like this. Did I do that correctly? Yes. So it's kind of just floating there. But the reason is they use this plastic shell, which it's screwed into. So, yeah, that kind of determines the distance and things like that. Oh, they have a screw hole here, which lines up with these. Yeah. So there's screw holes here, and those line up with these screw holes for the add-on PCB. We're not going to have such a nice plastic molded injection shell. We might have something 3D printed or something like that. I don't know. But I can't splurge for that, for this limited number, right? Yeah, so we figured out these mounting holes. That's very nice. I like that they had the drawings for that. That's awesome. Then we figured out, actually I thought it was going to be harder. We figured out the position of these mating connectors. So that's now basically done. And we can start populating our PCB. And we can choose, actually. We can choose if we want our components on the top, so over here, over here on the top, or we can choose if we want our components on the back. If we do it on the back, we'll be height constricted. So I think we're going to put all the components on the top. That would mean they might not be able to wave solder this, so these pins would have to be hand soldered during production. Yeah, you can use some more elaborate footprints for that. So footprints that basically break out to over here and over there, so that it becomes SMD instead of through hole. If we were going to make thousands of these, maybe that matters. Yeah, I don't know. It's going to be a complex board anyway, because this, you know, if these screw terminals over here and these over here, they're going to have legs on the bottom, which poke out the other side. So those would either also have to be manually soldered, and it has like X cost per pin, or wave soldered before this one is in there. Yeah, I guess they can wave solder it before this one's in there. No, because that would plug up the holes. Well, they can make a jig, but generally you don't want to make a jig for low volume count. And these need to go on top, because they can't go on the bottom, because they wouldn't clear. Okay. Well, let's try and keep the SMD components on one side at least, and then we'll figure out the rest. Yeah. But that's a pretty large. That's a pretty large PCB, because currently this PCB is now. Wait. Yeah, it's about 78 by 74. All right, that's pretty good. We can easily fit all these components on there. If you look at the size of the components and then the size of that PCB, that's probably easily going to fit, right? Yeah, we can easily put these all on there. We still don't have the right socket for this yet. We probably have to draw this socket. Or did we get the right socket? I don't remember if we got the right socket or not. I'll have to check that. I'll add a note. Check footprint socket. I don't remember. Yeah, but next time we can start laying this out, you know, making it somewhat logical. And we might also need to change these screw terminals or not, because we might want to have them facing upward instead of downward, to make it more wall socket compatible. And we currently have this size for the PCB, but that's going to stick out from the wall. I don't know how to do that yet. I'll get some European wall sockets so we can play around with that. And I might also get some 68 size wall sockets, because I'm building a new house and I can put any socket I want into the wall. So, I mean, I'd rather adapt my socket to this PCB, to this form factor, than have to do it the other way around. Yeah, we'll have to see. And maybe we can print a spacer so that whatever we mount into the socket fits into a standard European size socket. And then there's a little spacer ring that still makes a nice cover with the wall or something like that, right? Because I don't think this PCB size is going to fit in a European... in a European wall socket. So that might have to sit in front of it a little bit. Lots to figure out. But that's why we're here, aren't we? Okay, I'm going to close the PCB editor now. Yeah, save everything. This drawing was a great find. That makes things so much easier. And I mean, I don't really care about this measurement from the screw hole to the edge of the PCB. We're basically going to make that as tight as we can make it. Stupid question. Could you match the size of the board to their ETH RS485 board and just use their plastic? No, because I have this one. But this is also not going to fit in a European wall socket. And, I mean, this could work. Maybe. Yeah, because this is the RS485 version. Can we get the drawing for that? Let me check. No. Oh, wait. No. What do you mean, overkill? It's very nice. And they're really cheap. I mean, they did cram it in there. They even have a C6 in there. We're not going to use that, but that's fine. But they have an Ethernet IC in there. We're going to tap off of that. And yeah. And they have a 720 by 720 screen. This is actually a purpose the P4 is good for, because they can use the MIPI interface, right? So that in that regard, it's easier or better than an S31. Yeah. But I'm just going to use their board because it's cheap and they already make it. And then we're going to add on to that. But yeah, we were trying to figure out if we have a schematic for, or a physical diagram for this guy. But I don't think we have. Oh wait, the bottom board schematic. No, I don't want schematics. Oh yeah, sorry, yeah. It's the 86 blah from Waveshare, and they have a 720 by 720 MIPI screen on there. So it's a fairly high resolution touchscreen, and they have dual microphones in there already. Whereas they're over there and over here, and they have USB-C, they have Ethernet, they have a speaker even, an SD card slot, they have some power management on there, and it's a full P4 implementation. So they sell this for like 35 or 40 bucks. I can't make that for 35 or 40 bucks, not even close, baby. So I'm gonna steal theirs. And then we're just going to make a board that connects to their connectors and add PUE and all kinds of sensors and stuff. So yeah, that's the idea. Yeah, it's a nice touchscreen. So, but we're trying to figure out how we're going to do all the mounting and things like that, because this is not European wall socket compatible. And well, since I'm building a house anyway, I'm just going to ram other sockets into the wall. Well, I don't know. We might have to 3D print some adapter or something like that. I don't know. Killjoy Swixel. Yeah, sorry. I mean, I'd rather use a product of yours, but if I can't match the price, you can't either. So I mean, we're kind of in the same boat there. So better, I don't know, better join them than not, I guess. I don't know. Yeah. Anyway, we'll figure this out next time. Next time, Gadget. Next time. Yeah, okay. Anyway, that was another 3 hours. Whoa. Do we have any secrets? We can do some thermal shots of some boards that have been running for, I don't know, a few days now. If we can get the thermal camera online, that's always the question during the stream, right? Can we get the thermal camera online? So let's try that. We have my my E4, my very expensive, way too expensive thermal camera. Let's join it to my network. General Wi-Fi. I don't know. Let's toggle RTSP because, you know. Let's open thermal tools. They talk about another kind of world. Yeah, exactly. Unexpected Maker. Same for me. I'm not even going to try if they already have a product for that. Let's see. Can I connect? Maybe. Oh, it connected in one time. That is amazing. It's never done that. You're good luck here, Unexpected Maker. Thermal camera. Beam. Is that correct? Yes. Cool. Okay. So let's take our 24-volt board here, which is running with Ethernet. And let's see how warm everything is. Let me enable something here. Display settings. There. You guys can get a bigger view. Hold on. There. So the Ethernet IC itself is warm because this is a sandwiched board. The ESP32 is basically right below that. So it's a single 6-layer board. So it's running a bit hot, but not too much. But Nothing else on the board should be warm right now, because it's all being power fed from the other board. Okay. So we see a warm IC over there. That's my switcher going from 24 volt to 3.3 volt in this case, sorry. So 24 to 3. That's fine. And this is after running for a few days now. Yeah, so there we have our switcher and its inductor. And the inductor is 50-ish degrees. That's okay. Yeah, but these Ethernet ICs, they just run hot. The LAN 8720A, 7820A, whatever. Those generally run at 50 degrees anyway. And because it's sandwiched, basically it's this module here. Because it's sandwiched on the ESP32, so the ESP32 is here. These are the Ethernet pin sockets. This is USB-C. And it's basically one giant sandwich. Yeah, that whatever you're going to do, it's going to run hot. Yeah, but these are rated to run the industrial version, I believe 105. So we're nowhere near that. And the non-industrial version is 85, I think. Yeah, should in theory be fine. But it's warm. I'd rather have it cooler, but there is no way in any other construction I've been able to think of that is going to pass CE. Because if you have any length of pins connecting the clocks or the RMI signals, you're going to fail so hard. Trust me, I've tried. Yeah, there's not enough dampening you can do for it to survive a pin connection, basically. So yeah, the IC is hot, but the rest is okay. Yes, no, it's the other way around. The heat from the Ethernet IC, which has an internal regulator to 1.2 volt, I believe, is going into the package of the ESP. Right? So it's going straight into there. And that does make it run hotter. I mean, I get it. The whole board is like 45 degrees. But there's just not a lot of thermal mass there. I mean, it's not much you can do. But it's well within specifications. It's just hotter than I'd like, but there is no other way to do that. Now, on this board, it doesn't have the correct spacers, as you can see, because it's not sitting fully. On the production version, it'll have double height spacers, so there will be a bit more ventilation. Keep your hands warm in winter. Well, yes and no, because the second you put your finger on there, it's like 0.3 watts or something like that, right? So, yes, it's 60 degrees, but as soon as it has some kind of cooling whatsoever, there's not a lot of thermal energy there. It's just warm because it's, the rest is also warm. But as soon as it can, if it can duct the heat away, it's gone. Yeah, so. Anyway, this is a pretty tight sandwich. This will be fixed in production, so it'll have a little bit more breathing room too, because now the ESP module is sitting on the screw terminals. That's not ideal. I have a version here which has those pins, but I don't know where it is. But yeah, that'll be fine in production. But this has been running for 3-4 days, so this has been thermally soaked, basically, for the worst case scenario. Because if you run things with 5 or 12 volt, it'll run cooler. Yeah. And then we have a different board, which has also been running for a few days now. Let me see if I can get that under the camera. Maybe not. Probably not. Okay, I need to put these on my desk. My LED bars. My testing bars. Oh, there we go. So this is a different board that's also been running. This has been running from a low voltage intentionally, because it's a 5 volt power supply, but then it goes through various diodes and all kinds of other crap. And it ends up at 4.3 volts, and then I make it 3.3 volts, and then I up it to 5 volts again. But here we should see a diode that's warm. That's this one. Now that's not very warm at all, especially for a diode. They even do better if they run higher. But this should be a low drop diode. We can see how much voltage is dropping. That's actually something I wanted to test. Let me get the multimeter online. It's taking a while to boot. Okay. I haven't looked into a heatsink yet because basically it's okay as it is. But I might do that still. Okay, our multimeter is online. So we can see that if we take a ground and we probe the 5 volt terminal, we see we have 506 coming in, and then on Q power post over here it's turned into 4.6. So for unexpected maker who probably doesn't know this board, the outer screw terminals are all ground, so these are all ground, and then this middle screw terminal is actually VCC. Oh wait, let me, yeah. But that goes through several diodes and fuses and things like that, so that there's a lot of voltage drop there already. And then we're going through one of these diodes over here, and then we end up with 4.39 volts from the 5. But since we're making 3.3 volts, that's plenty for a modern switcher, basically. And we can see what our input voltage is. Yeah, our input voltage is 4.3, and our output voltage is 3.30 exactly. 3.31-ish. That's perfect. Yeah, sure. These are the mini modules. I'm not sure that helps or not. I think they used a smaller manufacturing process, so it can actually tolerate more heat. But yeah, it's the only way we could fit it on there. I'll look into heat sinks and see if we can ship it with a heatsink on there. That would actually be interesting. Did I want to measure more? Well, we're also making some 5 volt. Is this the 5 volt? No. Is this the 5 volt? Yeah, 5.12 volt exactly. That's perfect. So yeah, this IC probably doesn't show any heat. So here's our diode again. Oh, here's our Ethernet IC again. Here it is on a 6-layer board with nothing beneath it than ground plane on all layers, and with thermal vias and everything. Same IC, and it's running 46 degrees. So, I mean, yeah, it's running hotter on that big board, or in that small board, because there's just, there's only so much you can do. But, yeah, same IC, same configuration, 20 degrees cooler, sure, because there's just, there's a lot more mass here. This, so on the Ethernet board, this has an ESP32 with 8 megabytes of flash and 2 megabytes of PS RAM. And on the normal new ESP32, same configuration, also 8 megabytes of flash and then 2 megabytes of PS RAM. But this one stays the same. This one has 16 megabytes of flash and no PS RAM. But I'm working on some different versions, maybe. It is 4.3 because this is 5 volt, but it can also be 12 or 24 volt. So the input voltage through Q power post is variable by what power supply they're using, right? So this power board, it's currently sitting on top of a 600 watt 5 volt supply, but it could also be a 600 watt 12 volt or 24 volt. And then I need to deal with the power conversion on this top board. There is a different board, the Power 5HV, which is rated for 24 to 48 volt. Now this top board can't deal with that, so then the bottom board makes 15 volts, and then this converts it to 3.3 volts again. Yeah, so I'm specifically testing the lowest voltage it will be used at, because well, that's the worst case. We're testing both worst case scenarios, the highest and the lowest. I already did a 24 volt test with this, but then the diode drop, really, I don't care, right? But with 5 volt, if the diode drop would be, I don't know, 2 volt, that would become a problem, right? Because then we're below 3.3 volt. We can measure the diode drop. Let's see here. Yeah, we're dropping about 255 millivolts. Is that the right one? Let me check. Hold on. Yeah, it's the left one. Yeah. We can do it the other way around. But these are special low drop diodes. 253 millivolts. Yeah. So yeah, these are special low drop diodes. So 253 millivolts for a Scotchy diode is pretty low. Often you're in the 0.4, 0.5, even 0.6 value. But I use special low drops because I want to lose as little voltage as possible, right? Okay. That's probably also why it doesn't get that hot. I mean, 38 degrees is nothing for a diode. Yeah. Things sometimes just, if there's no thermal mass, it'll just run hot. Or if there's no airflow, or, I mean, you already had a fan in it for the LED panels. Maybe that also cools the PCB a little bit. But these LAN ICs, this one has an internal regulator, and that's why it's running so hot. I haven't made any designs with an external regulator for that. Maybe I could spread out the heat. Then again, this was already a challenge. I mean, where would I put it? It's already 6 layers. So, yeah. But this one now passes EMI and EMC testing. So, very happy with that. I used to have a switcher on there. Yeah, no. Like a 5 volt to 3.3 volt buck converter. It now has an LDO. That helped. Okay. Anyway, so these are all the V4 products. The other day I found a TVS diode from Toshiba that had a clamping voltage quite close to the working voltage. Surprised me quite a bit since it used... Yeah. Yeah, often the clamping voltage and the working voltage is pretty far apart. Yeah. Help cool... but turns out the high-res panels now generate more heat than the PoE Plus and S3. Yeah, LEDs are pretty mean. It's the most efficient way of lighting we have, but that doesn't mean they're very efficient. And I mean, it really depends on what type of LED you get. You can get like 200 lumen per watt or 240 lumen per watt for special high efficiency LEDs. But like these are more like 60 lumen per watt, right? And the rest is heat. And then if you make it even worse, if you go to 12 volt single addressable, yeah, you're just burning more watts. So, yeah, no. 5 volt is most efficient for addressable, and then even then it's not very efficient. So, yeah. Yeah, but I have my testing boards, and they've been running for a few days now. All fine, all stable. I might turn down the. Oh, you can actually do that real. We can do a test before we stop the stream. I guess we don't need a thermal camera right now. No, we do. We need to check the diode temperature. Let me put this on here. Oh, where do I put this? I guess over here. 4 point, no, I want to see the output voltage. Oh, I don't want to short anything here. Where do I have a good 3.3 volt point? I don't. Oh, maybe on the ESP. There. Okay, and now I'm gonna turn down the power supply. And I don't know when it will stop, but at some... Am I turning it down or up? The LEDs are getting dimmer, so I think I'm turning it down. At some point, it won't be able to regulate 3.3 volts anymore. I think it's getting dimmer. I don't know. I'm just turning the knob. Oh, it doesn't turn any further. Okay. So I guess we now need to measure the input voltage. 4.1. But that's before the diode drop. So after the diode drop, we're at 3.86. So on the input capacitor... Yeah, the input capacitor for the buck converter is now getting 3.8. But what is it on the power supply? 4.5. Okay, yeah. That is basically also what I've spec'd it for. Everything should still work with 4.5 volt in. Because if you hit a very large transient, the power supply may take a little bit to keep up. And it might voltage sag. Now, on this one... We have these 3 times 12 gauge between the power supply and the power board because we want to support up to 50 amps. Or is this 10? Oh no, it's 3 times 10 gauge. I think wiring wise it'll be okay. But yeah. So let's put that back to 5 volt. But it hasn't crashed yet. That's good. Right, there. There. Okay, let's put that back. Oh. $5.11. That sounds good. That's 5 volt-ish to me. Oh, we didn't measure how warm the diode got, but, I mean, I can't imagine that making a difference. It's now 38 degrees. Yeah, I don't care. Okay, and because with a higher voltage, like 12 or 24 volt, the diode will only be cooler, right? So, won't matter at all. Do we want to do another test? Sure, let's do another test. Where is this cable going? Into the rest of the mess. Let's do some dangerous stuff. Here we have a USB power source. Because that's basically why the diode circuit is there. We're going to plug this into the USB-C. Okay, it's actually going to draw a bit of power because probably this voltage is higher than what is getting through Q power post. I mean, yeah, that's because it has protections. So it kind of switched over to running from this power source now instead of this power source. So now I can just turn off the power supply. Let me... yeah, I need to turn off the right one. Hold on. So let me show you the bar, and I can pull this one out. Okay, so now power supply is off, but you can see the draw from the USB is still continuing. If I put the power supply back in again, it's still doing the pattern, so it didn't reboot. Right, so clock, you heard it turn off. You can see the power draw from the USB socket. And if I turn the power back on, power's back on. And it didn't reboot. So that's good. So that's, I mean, it's rudimentary power input switching. My other boards do it differently. It depends on what board we're talking about. But that seems to work fine. So we can just switch power sources, no problem. That's all protected. and no reverse flow and blah blah blah. Cool. Okay. Yeah, so that's V4 Dig Octa brainboard, and so far working great. Very happy with that. You don't get many options. Yeah, and 1010, yeah. 12,620 LEDs. Yeah, I mean, as I said, sometimes it's just going to generate heat, whatever you do. It's just what it is. It's physics, right? And at some point, maybe in 10 years' time, we'll have LEDs that are twice as efficient, or ICs, because those little ICs, each little IC, how minute ever-wise it is, even if it's off, it's still drawing power, and it's still converting power, and it's still getting warm, right? So, yeah. What happens with USB-C connected and you wire up the power supply in reverse polarity? Well, A, you're an idiot, and B, there is a fuse for USB-C here. There's a fuse for Q power post here. There's a fuse for the multiple input here. And then they each have their own diode, and Q power post even has multiple diodes in the circuit. So in theory, you might trigger a PTC, might not. I don't actually know. But in the end, the fuse will probably block, or the diode will block, and then everything keeps running. Or it'll probably reboot, but you know, yeah, I'm not too worried about that. So I mean, everything has diodes and PTCs, and yeah. Yeah. If you wire up the big board in reverse, you'll blow. No, yeah, you might blow some of these, but it also has 3 input fuses, 1 per wire, so that you can't overload a single wire, right? Because we have a 3-wire connection to the power supply, but who says all power is going to distribute evenly? If you make this cable twice as long as this cable, well, I know where the power is going to flow. NVIDIA somehow doesn't know, but I do know. So that's why we have 3 individual input fuses. A PTC and protection at the USB end. Yeah, everything's... Nah, I design everything with loads of protections. It has TVSs on the data lines and the power line. It has a PTC. It has a diode. Don't worry. Yeah, but I mean, NVIDIA, I figured this out years ago, that if you want to distribute power over multiple cables, which is okay, that can work, you want a fuse per cable, because I don't know how the power is going to flow. If you do something stupid and use an 18 gauge and a 22 gauge and a 16 gauge, I mean, yeah, but in this case, it has some fuses in there, so if you overload a single wire, or you cut 2, or they come loose, or I don't know, whatever horrible scenario happens, it'll just pop the fuse done. Yeah. Ah, okay, no, well, I've been doing this for a while now. No, also on these boards, the USB socket is fully ESD protected on both power and data pins. I don't have ESD protection on the CC pins. I don't know if that's needed, but... Do you have ESD protection on the CC pins, Unexpected Maker? Well, we'll use some thick film resistors, and then they can carry the brunt. I don't know if I use thick film. I guess most resistors are thick film nowadays. So, yeah, should be fine. Yeah, I think so too. No, don't worry. I mean, all the other ports also have ESD protection. I mean, did you see my level shifter stages here? This is just a single level shifter times 8. So it has ESD and over voltage protection. So I don't know what you need to do, but if you short these with 48 volt directly, it's still fine. Yeah. So yeah. I don't have ESD protection on the microphone though. That might be a problem. Yeah. Oh, I might actually add it to the I2Cs. I2C also doesn't have ESD. Well, officially, if you follow the CE guidelines, any port they can poke with their ESD gun needs ESD protection. That's basically what they do in the lab. So they have this giant gun, and the gun has a tip like somewhat like a screwdriver, like something like this, right? But then blunt, more blunt, even bigger and blunter. And if they can poke at it like this, they'll zap it with 2 kilovolts. And this connector over here, this one, it's a JST PhD and a PH and a PhD, so double and single. They might zap those because they might consider those exposed pins, except if you have an enclosure and they can't reach it, then they won't zap it. Because if they zap an ESP pin, it's dead instantly, right? So if you have some GPIOs or some I2C pins like over here, and they zap one of those, your ESP is dead. Instantly, one zap, it's done, you failed CE. No, it doesn't matter. It doesn't matter when it's exposed. If they can zap it, they'll zap it and instantly kill your board. You failed. Come back next time. So, yeah. So this connector, that's what we were talking about. The Stemma QT, what is it? The PH? No, that's not PH. SH? I don't remember. This one actually has very shallow... The contacts are all the way on the back, and there's basically no way you can get your finger in here to touch the pins, and that basically means that they can't easily zap it either, and for then CE testing, you basically get a pass. Now, functionality-wise, I don't know if you want it or not. That's a different discussion. But for CE testing, they need to be able to touch the pins, basically. And if they can touch the pins, they'll zap it. And, well, I had a board like this, right? Like a pin header. And they were like, oh, this is exposed. Zip! Dead ESP done. Instant done. Over. The test failed. Please pay at the front desk. Goodbye. Yeah. Anyway. That was fun. I did learn, it did teach me what I need to protect and what I didn't. So, I think the connectors like this for cables and stuff, it's fine. Unless they're going to be hot plugged. That's a different thing, but yeah. Yeah, it doesn't. That's partly why these now have ESD and over voltage protection. In the latest tests for the V4 stuff and for Dig Next, for instance, we killed 7 LED strips, but no boards. So my boards survive the ESD surge, but the connected LED strip doesn't. So yeah. How these strips are then CE certified, I don't know either. But yeah, it's even in my own strip is also CE certified, but it's a different certification for the strips. And in those tests, they did do some ESD testing also, and they used the Dig Next 2, and the Dig Next 2 survived perfectly fine again. But the strips, you know, the WS28, 14, whatever, yeah, they just die. So later, Unexpected Maker, thanks for joining. I'm also going to go. I'm going to leave this running for a little while longer. And I thank everyone for being here for yet another design session. Next time we'll continue with more layout on the PCB and fixing maybe some Ethernet socket footprints and things like that. And then we're going to get closer and closer to being able to order a prototype. Very exciting. So hit the like and join next time. Thanks, guys. Bye-bye.